Let's begin. So, what did we just achieve? We just achieved an area formula for the area of a triangle given two side lengths and the angle at which they meet. The formula that we get, all right, here, let's fill it in again. If B and C are sides of a triangle meeting at an angle of alpha, then the area of that triangle is 1/2 the product of those two sides times the sine of that angle. Nice. So what we're going to do today is we are going to use that fact to compute the area of the triangle 3 different ways. Right, there are 3 different angles we could use to compute the area of a triangle. They should all give us the same result. So that tells us that there should be some sort of relationship amongst the sides and angles of the triangle, because no matter which of these corners we use to compute the area, we should get the exact same result. So let's go ahead and do that. So let's prove the law of sines. So let's compute the area of this triangle 3 different ways. And maybe there will be some light color coding. So if we focus at this corner, using those sides, we will get a formula that the area is 1/2 B times C times the sine of A. And that's verbatim the same as the formula we just wrote down. But that's not the only corner we could use. We could also use this corner. There's one of the sides adjacent. There's the other one. That will give us an area formula of 1/2 AC sine of B. Finally, if we use the other corner, that corner, the corner labeled C, with that edge and that edge adjacent, we will see that the area is 1/2 AB sine C. Right, in each case, it was the product of two adjacent sides and the angle at which they meet. Each pair of those should give the area. Oh, I forgot to say 1/2. But all of those give the area, so all of those have to give the same result. So let's see what that means. Close parentheses there. So no matter which pair of these we use to compute the area, we'll get the exact same result. So that means, say, these two formulas have to be equal. So it must be that 1/2 BC sine of A is equal to 1/2 AC sine of B. And notice on each side, I just see a bunch of stuff multiplied together. And none of those things are 0. If any of them were 0, I wouldn't have a triangle, now would I? Triangle can't have a side length of 0, it can't have an angle of 0, else it's not really a triangle. So that means we can do some canceling. Both the left and right hand side are multiplied by 1/2. So we can cancel those. Both the left and right hand side have a C as a factor, so we can cancel those factors. So by canceling 1/2 times C, we will see that B times sine of A is equal to A times sine of B. And on the one hand, you could interpret that as being a final answer. I'm going to go ahead and say that I want to do something different. I want to sort all of these formulae alphabetically. Where alphabetically just means I want all the A's on one side, I want all the B's on the other side. So if I want all the A's on, say, the left-hand side, it looks like I will need to divide both sides by A. And I want to move this B to the other side, so I'll need to divide both sides by B. So if I divide both sides by A and by B, or by A times B if you prefer, you will wind up with sine of A divided by A is equal to sine of B divided by B. So, law of sines. So here's 2 thoughts of what the law of sines says. Given a triangle with side lengths A, B, and C, with angles A, B, and C opposite the sides labeled A, B, and C, we get the following equalities. We get that sine of little a divided by big A is the same size as the sine of little b divided by big B. Now we could do the same thing centered at using another pair. I know that these two things are equal. We can go and do the same sort of thing with that. So here's what I'm going to tell you guys to do. Pause the video. Write down 1/2 AC sine of B is equal to 1/2 AB sine of C. Take those equations, solve them all down till you can put them in the same form as this equation, and see what you get. So, let's do that. You all just did already, so presumably you're just going to watch this part really, really fast. So what can I cancel on both sides? Well, I can cancel the 1/2, and I can cancel the A. So by canceling 1/2 A from both sides, left with C times the sine of B is equal to B times the sine of C. If I divide both sides by B and by C, I wind up with sine of B over big B is equal to sine of little c divided by big C. So that gives me the remaining claim. The sine of B divided by B is equal to the sine of C divided by C. So the sine of B divided by big B is equal to the sine of little c divided by big C. So what does this say? Given a triangle with side lengths A, B, and C and angles A, B, and C opposite, we see that sine of A divided by A is equal to sine of B divided by B is equal to sine of C divided by C. So what is this saying? This is saying a ratio of sine of an angle to the side opposite is the same for all three corners of a triangle. And maybe I'll go ahead and remark, we could have written this another equivalent way, which I would also call the law of sines, and depending on exactly what context you're in, maybe it would be more useful. You could also say that A divided by sine of A is equal to B divided by sine of B is equal to C divided by sine of C, right? Just taking the reciprocal of every term of that equality. So those three things are also all the same. So you can use the law of sines to determine some unknown information given a triangle. So here's one. Let's suppose you're given a triangle, not drawn to scale, which has an angle of pi over 6, an angle of pi over 4, a side length of 3. Is that enough information to figure out the rest of this triangle? So what the law of sines says is as soon as you know a side and an angle opposite, you can use that information to compute everything else. 3 divided by sine of C will be the same thing as B divided by sine of pi over 4, will be the same thing as A divided by sine of pi over 6. You'll notice in each one of those terms, there was one thing that I don't know. So it would be hard to use that to solve anything. So there's one thing that we'll need to do first. We will need to determine that this angle C. And well, that's not so hard. What do the three angles inside of a triangle add up to? They add up to 180 degrees, or in radians, because I'll prefer radians, pi radians. So the first thing that I will use is pi over 6 plus pi over 3 plus C is equal to pi. Oh, pi over 4. I could solve that for pi, right? It looks like the common denominator will be 12. So solving that for C, I'll see C is equal to 12 pi over 12, because this is equal to pi. And now I need to subtract these two from the other side, subtracting pi over 6. So that'll be minus 2 pi over 12, because that is pi over 6, minus pi over 4 is 3 pi over 12. Hey, I can solve that for, well, it's not a matter of solving, it's just evaluating now. I see 12 pi over 12s, minus 2 of them, that'll leave me with 10 pi over 12, minus 3 more will leave me 7 pi over 12. So so now I know what that angle C is. So let's erase that. That highlighted bit. Well, now let's look at what the law of sine says. So the law of sines says that the sine of C, 7 pi over 12, divided by the length of the side opposite, 3, is equal to the sine of pi over 4 divided by capital B. Hey, capital B is the only unknown left in that equation. I can solve this for capital B. So I guess that will just require me to multiply B over to the other side, multiply 3 over to the other side, divide sine of 7 pi over 12 to the other side. That will give me B is equal to 3 times the sine of pi over 4 divided by 7 pi over 12. Sine of 7 pi over 12. The sine is important. Sine of an angle is not that angle. Cool. Well, let's just wrap this up. So on the one hand, there's an answer. I don't know what the sine of 7 pi over 12 is yet. In the next couple of lectures, once we hit angle addition or the half angle formulas, we'll have the ability to compute that. But for now, let's just get a decimal approximation. So let's go ahead and grab that. Okay, we're back. So, asking the Google calculator to compute the sine of pi over 4, notice it even says explicitly in radians, that's good. Divided by the sine of 7 pi over 12, also in radians, that's good, results in approximately, let's say 2.20. Nice. So here's what I want you to do now. We found almost everything, we still haven't found the side length A. Pause the video, find the side length A, and then come back and then we'll do it together. Okay, good. You've just computed A, you got whatever it is that you got. Let's do it together now. So, same thing. Also by the law of sines, I'll switch colors. Sine of 7 pi over 12 divided by the length of the side opposite, 3, is equal to, and this time I want to figure out things about A, so I will use that opposite pair to find that information. Sine of pi over 6 divided by A. Again, can we solve that for A? Of course we can. We'll wind up with A equals 3 sine pi over 6 divided by sine 7 pi over 12. So again, we're resorting now to a machine. Well, I'll even do this live because there's very little that I need to change. The only difference is that pi over 4 should now be a pi over 6. Somewhere around 1.55. Nice. So check that out. Check out what we've just pulled off. Given 3 pieces of information, given this angle, that angle, and that side, so given angle, side, angle information about a triangle, we computed all of the other information about the triangle, the remaining angle, and the 2 sides. How did we do it? Well, so in general, whenever you know 2 angles and 1 side of a triangle, step 1, well, what did we do? We found the remaining side length. We use the fact that angles add up to pi radians, or 180 degrees if you prefer, to find the remaining angle. So step 1, use that angles in a triangle sum to pi radians, or 180 degrees, to find the remaining angle. step 2, use law of sines to find the remaining sides. Nice. So the other type of situation you might be in is maybe you're in a situation where someone has given you two side lengths and the angle at which they meet. So, for example, maybe they've given you this much information. 10 degrees, 325. That's enough information to compute the area of the triangle, but if you think about using the law of sines, B, C. What are the terms you see in the law of sines? You see sine of C divided by 3, so there's an unknown there, there's a C there, divided by sine of 10 degrees divided by A. Well, there's an A there, so there's an unknown there, is equal to sine of little b divided by 25. There's an unknown there, so no matter how you write the law of sines, there are two unknowns in the equation you would want to solve. It's hard to solve an equation with two unknowns instead of just one. So instead, I'll resort to the so-called law of cosines, which the next lecture is devoted for. So we will be able to solve that using the law of cosines. A side-angle side-side angle triangle. So this is an ambiguous situation. We'll explore it a little bit later. But let's do an example. So if I give you a triangle that satisfies this information, can you figure out everything about that triangle? Well, let's see if we can. Let's try to solve this for the angle little a and the angle little c. Well, let's just see. So I guess first we'll try to find sine of c. So let's write down something that will tell us sine of c. So apparently by the law of sines, I know that the sine of c divided by the length of the side opposite, 4, should be equal to the sine of any angle divided by the length of the side opposite. Let's see, there's an angle, there's a side opposite. I know those two. So sine of c divided by 4 is the same thing as the sine of pi over 2. How did I do? Pi over 6. Divided by the length of the side opposite. What length is opposite the angle of pi over 6? 3. Well, hey, I can solve that for c. I know exactly how to solve that for c. That will give me sine of c is equal to 4 times the sine of pi over 6 divided by 3. Oh, but hey. What's the sine of pi over 6? That's an angle that you see on the unit circle. Sine of pi over 6 is 1/2. So that's 4 times 1/2 divided by 3. That's 2 over 3. Groovy. That's progress. I know what sine of c is. So now ask yourself, I want to know what c is. That's what sine of c is. Sine of c is 2 pi over 3. Nope, just 2 over 3. So now let's try to find c, right? I need to know what c is. That's the goal. I don't want to know what sine of c is. I want to know what c is. But I know how to solve sine of c is equal to 2 over 3. I know how to find all of the solutions, right? One of the solutions is given by inverse sine. The other one is given by pi minus inverse sine. The other one is by adding an arbitrary multiple of 2 pi to those numbers. But I don't want all of the possible angles. What angles can I see inside of a circle? Well, for example, I couldn't see an angle of like 375 degrees inside of a circle. The three angles of a circle have to add up to 180 degrees, or pi radians. So every one of them is at most pi. The biggest angle you can't see an angle of 180 degrees inside of a triangle. An angle inside of a triangle is less than 180 degrees. So how many angles between 0 and 180 degrees, or between 0 and pi radians, have that as the sine of c? And in order to see what the answer is, see how many there should be, let's draw a picture. So there's the unit circle. Here is a line, because sine is the y value. So I'm going to draw a line at y equals 2 over 3. It looks like there are two. There are two angles. And in fact, we know how to find them. This one is given by arcsine. This one is given by pi minus arcsine. So there are two such angles. One of them is inverse sine or arcsine of 2 over 3. The other one is pi minus arcsine of 2 over 3. Let's go ahead and approximate those, again, using a machine. Arcsine of 2 over 3 is somewhere around 0.73 radians. And you know what, that word radians isn't necessary. When you don't specify a unit for your angle, it's assumed you mean radians. The other one is pi minus that. All right, and we're back. So it looks like that is somewhere around 2.41 radians. And let's go ahead and point out this one is acute. So what does acute mean? An angle is acute if it is less than 90 degrees. So that's less than pi over 2 radians. So pi over 2 is like 1.5-ish. That's less than 1.5-ish. This one is obtuse. And we can see that over here as well. If you saw that angle inside of a triangle, you would say, yeah, that's an acute angle. If you saw this angle inside of a triangle, you would say that is an obtuse angle. It's bigger than 90 degrees. So how many choices of C are there? There are two of them. They're there. If we wanted to find the remaining angle inside of a triangle, well, what would you do? You would say, well, I know what C is. I know what pi over 6 is. The three angles of a triangle have to add up to pi radians, so you can compute A. So let's compute them in each of the two cases. So let's see, when C equals arcsine, sine inverse if you prefer, of 2 over 3. Well, I know that A plus pi over 6 plus C has to add up to pi. So I can subtract pi over 6 and C to the other side and get A is equal to 5 pi over 6 minus C, which, again, we can approximate. Okay, here we are. 5 pi over 6 minus the inverse sine of 2 over 3 is approximately 1.89. Entering that in. And again, notice, this is an obtuse angle. The final the final option is, let's see what happens when C is equal to pi minus arcsine of 2 over 3. Let's see what we get. Well, we'll wind up with the same sort of equation. This equation, A equals 5 pi over 6 minus C. Oh, there was a mistake here. Is approximately 1.89 radians. I didn't include the exact answer, did I? So let's include the exact answer. This one I gave is a decimal approximation. The exact answer is 5 pi over 6 minus arcsine, or inverse sine, of 2 over 3. positive 2 over 3. The remaining one, in the case that c instead is pi minus arcsine of 2 over 3, well, let's write down what that is. That is 5 pi over 6 minus pi, let's put the parentheses in, pi minus arcsine of 2 over 3, because that stuff inside the parentheses, that is c in this instance. And let's work out what that is. 5 pi over 6 minus pi becomes negative pi over 6. Distribute this negative sign over those parentheses. You'll get a double negative there, which will become positive, plus arcsine of 2 over 3, maybe simplifying a little bit, arcsine 2 over 3 minus pi over 6. Let's see what that produces. Here we are. It looks like that angle is somewhere around 0.21 radians. Oh, come on. So again, for emphasis, this first one, in the case that c is equal to arcsine of 2 over 3, we end up with this angle, which by computation is obtuse. When you use an angle of c equal to, so that was in this case. So this is in the case that c is acute. In this case, c is obtuse. We worked out what a is. We got a to be acute. Nice. So that reveals what angle little a and little c are. I guess you might say, well, I still need to know what the side length a is. I think I don't want to. Well, you know what? It's not like I need to be careful with time management. If this were in class, I wouldn't bother finding the side length a, because it's not even one of the items listed. But let's find the side length a. So is there a pair consisting of an angle and a side opposite that I do know? Yeah. I know 3 and pi over 6. So 3 divided by the sine of pi over 6 is equal to the side length a divided by the sine of a. And there are two cases again, but I can just work out what both of those are. So that means that a equals 3 times the sine of a divided by the sine of pi over 6, but I know what the sine of pi over 6 is, it's 1/2. So this will be 6 times the sine of angle little a, when a equals 5 pi over 6 minus arcsine of 2 over 3. What do we get? Well, let's use a machine to plug it in. Here it is in that case. It looks like I get that side length is approximately 5.7. In the case that little a is, so the other case was arcsine minus pi over 6. Let's write down what we get. Here we are. It looks like we get approximately 0.20 as that length. And let's go ahead and see if this makes sense. So that was using information about a. So in the case that a was an obtuse angle, the side length a was very big. And that's what you expect. The side length opposite an obtuse angle is going to be the longest side of a triangle. In the case that a was acute, in fact a pretty small acute number, that's around like less than pi over 10 radians, you get a very short side length for a. Nice. So in the case, so here's the takeaway. For a side angle triangle, there may be two or no solutions. So, time for a minute, let's close it up. Let's see a situation in which there is one solution, because that is also possible. So let's try to solve this triangle. So let's follow the same instructions. So the sine of little c divided by 1 is equal to the sine of pi over 6 divided by big 3, by the number 3. So that gives me the sine of c is equal to 1/2. Sine of pi over 6 is 1/2 divided by 3. Well, I can write that. 1/2 divided by 3 is 1/6. So then you'll check for possible answers. So the options are c is equal to sine inverse of 1/6, or c equals pi minus sine inverse of 1/6. But let's, I claim that one of those is obviously wrong. So drawing a unit circle. So there's the one that's coming from sine inverse. There's the one that's coming from pi minus sine inverse. So if you check it out, that angle is obtuse. Right, if I were to draw this triangle, you would say, yeah, that is an obtuse triangle. So in the case that C, this angle C, is obtuse, that would have to be the longest side length, because the side length opposite an obtuse angle has to be the longest side length. But it can't be, right? 1 is not longer than 3. So here's the observation. The side opposite C is not the longest side. So C cannot be obtuse. We conclude that C is equal to sine inverse of sine inverse of 1/6. Whatever that happens to be. I won't get the decimal approximation this time. But what could you do then? Once you know this angle, so once you know that that angle is the inverse sine of pi over 6, you can find this angle by saying, well, the 3 angles have to add up to pi, so you can solve for A. Once you know that, you'll know an angle and a side opposite. There's a side you know the angle opposite. You can use the law of sines to find the side length big A. So I won't, but you should consider doing it if you want more practice. So I'm going to end this video in a moment. Let me just tell you what the next video will be. It will be applications. So here are the applications. So you and Katrina Allen, the top-ranked US PGA player, as of May of 2019, stand in a field precisely 30 feet apart, and you see a flying saucer pass overhead. The triangle below summarizes what you see. So you're standing 30 feet apart. You see a flying saucer. Let's see how I can draw. There. It's a flying saucer. Passing overhead. Let's give it motion lines. It's moving. You would like to know lots of things. You want to know, how far are you from the flying saucer? So what is this side length? You would like to know how far Katrina Allen is from the flying saucer. You would like to know this side length. You would like to know how far over the ground is that flying saucer. What is this side length? So, Check it out. That's exactly a situation where you're trying to solve a triangle. The red question mark is the side length of the triangle. You know angle side angle for that triangle. So you can use the algorithm that we gave a few moments ago to solve it. Similarly, purple is the side length of the triangle. The yellow line is just the height of that triangle. You should be able to find that using some trigonometry as well. Second question. So you and Zebulon Pike Jr. Stand 50 feet apart and look towards the top of a distant mountain. Mountain might not be the right word. I think it works out to not be that tall. These are all, of course, bull plop, to not swear on the recorded video, examples, and so the numbers are all made up. They don't mean anything. So in this situation, can you do the surveying by taking two different angle measures at a known distance apart to determine the height of a mountain? Well, let's do that in the next video. I'll talk to you in a moment. Have a good day. No, I'll see you in a moment. You watch the next video almost immediately. Ciao.